Greetings everyone, and welcome to the last topic in section 4.2. This video is all about contingency tables, which is one way of representing data. Let's look at an example. Suppose we survey students in Stat157 to find out whether they like coffee and whether they like spicy food. Once we've taken a show of hands or something like that, then one way that you can represent that data is in the form of a little table. So let's do a little table here. Where we label the first column as like coffee and the second as don't like coffee. And I am definitely in that second column. I do not like coffee. And then there's like spicy food. And I very much like spicy food. So I would be basically in the top left corner here, or top right corner. So like spicy food and don't like spicy food. And let's say people showed hands and the number of students who like coffee and spicy food is 13. The number that don't like coffee but do like spicy food is 5. The number who like coffee but don't like spicy food is 2. And the number who don't like coffee and don't like spicy food is 4. Of course, these are just made up numbers, but let's say that that's where we are. And then we can start answering questions like, for example, finding the probability that a student likes coffee, that they like coffee but don't like spicy food. We can find a bunch of probabilities, or we can find out numbers, raw numbers of students as well. Okay, so because this is our first example, let's take a look at a couple of different ways of understanding this data. The first is, if we're going to be talking about this later, it's kind of nice to have some abbreviations. So let's let C equal coffee, and then the not coffee column we'll call it not C, and then like spicy food is S, and then don't like spicy food is not S. And this number 13, for example, is then the number of people who like coffee and like spicy food is 13. And so you could find things like the probability of liking coffee and spicy food. It's going to be the number who like coffee and spicy food divided by the total. Now, in order to find the total, you'll want to add up all of the students. You can see that we have a total of 13 plus 5 plus 2 plus 4. So if we take all of those numbers and add them together, then we can write out that the total is 24 students. So then our probability of being a coffee drinker who likes spicy food is going to be, well, we found that the number of coffee drinkers who like spicy food is 13, and the total number of students is 24, and so we have our fraction. Now, if you like, and this is optional, you can express the same data in a Venn diagram. So for example, you could draw a little Venn diagram here. With two circles like this, where this is coffee, and here's our spicy food. If we just replicate, I'm just going to draw our little table over here again so we can refer to it directly. So here's coffee and not coffee, and spicy food and not spicy food. And we had 13, 5, 2, and 4. Then the centerpiece here, the overlap, would be the people who like coffee and spicy food, and so that would be 13. All right, why is my tablet not wanting to write here? There's 13. In other words, This table entry is the one in the middle. This table entry over here is the people who like spicy food but not coffee. And so that would go over on the right, spicy food and not coffee. And circling the people who like coffee but not spicy food would go to the left inside the coffee but outside the spicy and be here. And then that last entry would be on the outside, people who like neither coffee nor spicy food. So let's do some follow-up questions. For example, we could calculate things like, what is the probability that a randomly chosen student likes coffee? One way of writing this would be probability of coffee. We want the number of coffee drinkers divided by the total. And if we look at our table here, we know that the total is 24. We figured that out before. It's just the sum of all of those. But the coffee drinkers then would be the sum of the first column, all the coffee drinkers here, and that would be 15 divided by 24. If you like, you could also do the following. If you prefer, you could say the probability of coffee drinking is equal to the probability of coffee and spicy plus the probability of coffee and not spicy, and those together make the coffee drinkers. And so if you insist, you could say that that's 13 over 24 plus 2 over 24, and that again gives you 15 over 24. What is the probability that a randomly chosen does not like coffee? Well, you could either do that directly, saying that the probability of not coffee is just the number of students who don't like coffee divided by the total, but I also want to remind you that the probability of not coffee is equal to 1 minus the probability of coffee, because they're complements. And we just found that, so it's 1 minus 15/24. And if you do a little fraction work, that's 24/24 minus 15 over 24. And so you get 9/24. Of course, you could just go to your table and add up all the entries in the rightmost column that don't like coffee, and that gives you 9 out of 24 as well. And either of those is a perfectly fine way to go. One last example. What is the probability? Or one last part to this example, rather. What is the probability that a randomly chosen person, a chosen student, likes coffee or spicy food? And I'm just going to redraw our table yet again so that we know what we're looking at here. We're going to have coffee and not coffee, spicy food and not spicy food. And then in our table, we're going to have 13, 5, 2, and 4. So in order to do this, there's a couple of ways to go. The first is to say that the probability of coffee or spicy food will be equal to the total number of students who like coffee or spicy food divided by the total. And then we have to go to our table and identify all of the coffee drinkers or the spicy food lovers. And so this first entry in the top left, the 13, falls under both. The entry below it, these are coffee drinkers who don't like spicy food, so they do fit into our category restrictions. And then the 5 in the upper right is also someone who likes spicy food, so they're included in our count. And the only one we've left out is the bottom right, which is neither coffee nor spicy food. And so if we add those up, we're going to have 13 plus 5 plus 2 divided by 24. And if you add that up, that's 20 over 24 equals 5/6. So when you're reporting your answers, you should either give them as a reduced fraction or a percentage is also fine. Now, if you prefer, there's a different method. So if we call this method that we just did method number 1, then method number 2, you could also say that the probability of coffee or spicy food is equal to the probability of coffee plus the probability of spicy food minus the probability of both. So the probability of coffee, if we add up the entire first column, we're going to get 15. And so we get 15 divided by the total, which is 24. And then if we add up all the spicy food, we're going to get 18 here. So we're going to get 18 24ths. But when we've done that, we've double counted the coffee drinkers who like spicy food. So we have to subtract the overlap, and that's 13 over 24. And 15 plus 18 minus 13 gives us 20 over 24 equals 5/6 as before. Also, if you wanted, method number 3. The probability of coffee or spicy food is 1 minus the probability of that negation. And we know that that's 1 minus the probability of not coffee and not spicy food, using, of course, De Morgan's. And then we get 1 minus, and then I'm just going to scroll up for a second. The coffee and not spicy food is going to be this entry here, the 4. And so we're going to have 4 24ths. Doing a little fraction work, this is 24 24ths minus 4 24ths, and that gives us 20 24ths equals 5/6 as before. So there you have it. Many different ways of coming up with the same answer.